So first I would like to thank you for the organizers for inviting me to this such a nice event. So I am Hossein Azizpour. I will start as an assistant professor in machine learning from January at KTH in the robotics perception and learning group. This talk is about our recent efforts in the group that I will be joining there, including Kevin Smith and Josephine Sullivan and Professor Emeritus Stefan Carlson. So the title of my talk is If the High Accuracy of Deep Learning Models Enough. So I intentionally put the high accuracy and enough in quotation marks because it could have different meanings depending on the applications or field that you come from. So maybe the better question to ask is, or the more accurate one is to say, if accuracy is the only thing that we care about when dealing with machine learning models, especially deep learning in this case. So before discussing that question, I will reiterate the classical definition of machine learning. Arthur Samuel gave the very old definition, which was basically to put machine learning in contrast with more traditional AI methods by coining the terms like data and learning in this definition. Later on, a more formal definition came by Tom Mitchell, which focuses on saying that a machine learning model needs to be able to use experiences to improve the performance as measured by a specific performance measure P for a certain task T. So again, experience, data, performance measure, accuracy, things like that, and learning from data. So although different ML practitioners or theoreticians don't necessarily agree on the same definition, they all have maybe the two terms data and performance in their definitions. Data is to contrast with explicitly programming the rules in the model. And the second term, performance, is that actually you have a measure, you define what kind of aspects you're focusing on for this model, and you want to improve by harvesting data and mining it and analyzing it. But how good is that definition for practical purposes? That's the question of this talk. So in overview, I will first generally talk about what things we might be potentially interested beyond the accuracy. Then I will focus on one of our recent works on getting our uncertainty from pre-trained deep networks with batch normalization. And then since I work also in Science for Life laboratory, I will give a brief overview of how we use this uncertainty for a medical project which we have on breast cancer and mammography. So I'm sure you've seen lots of papers, lots of talks, you've read, and on the news everywhere that deep networks have astounding performance. This is true for many different fields, and especially from where I originally come from, which is visual object detection. Up to 2012, before this resurgence of deep neural networks, it was very common to publish a paper by 1–2% improvement on the accuracy, and even without showing there is a significance in this improvement. While after that, we are now more used to like tens of percentage points in accuracy improvements. This is not completely true for other fields, like for example, maybe NLP, which requires more high-level logical reasoning. So maybe it's better to call it deep networks have astounding performance at supervised prediction. For example, in sentiment analysis in NLP. But is that enough? So that's the question. So the short answer to that is kind of obviously no. And the reason is because it's almost impossible to always know about the random variables that involve into our prediction system. And even if knowing that, it's hard to embed them in our performance measure that we have our system optimized on. So for these reasons, we need to be able to be robust to the cases that we haven't either thought about or we haven't embedded in our performance measure. To give some examples from the applications, we know about self-driving cars. So maybe if you ask somebody what's the point of a car, is to move from point A to point B, then the autonomy here may be the main performance measure. But we know that, for example, last year with Tesla's Tesla car Model S, there was an incident that there was one casualty because of the bright weather and a white part of a tractor which came into the highway. And both the driver and the machine learning model were not able to detect it because it was a very rare scenario that happened. Or in surveillance systems, we want to, maybe the accuracy is to do the best face recognition or identity recognition, or the activity of people who are exposed to that camera. But at the same time, and that's our performance measure, but at the same time, we want to be robust to adversarial attacks, to impersonate people. Another example is in communication. Imagine that you want to use a machine learning system to compress your data, streaming data based on their content, and the measure is normally the average compression, how good that compression is. But then in practice, actually, other things might be important. For example, the worst case scenario, if a video the content is absolutely non-compressible, you don't want to jam the system, right? Another example is in financial technology, where there is a time involved where the trends and patterns change. So this is something like, we usually measure our performance assuming that the distribution of data is going to remain the same over time. And which we know that in financial scenarios, it's not like that, and the model should be able to adapt to new patterns and recognize new trends. Of course, in sensitive domains, so many things become important, like in medical science. We need to have very robust systems which make low rate of mistakes, but also knows that when it's prone to make mistakes. Also, we want to have a explanation giving to the patient, but also the physicians involved, that why the system made such a decision. So in more general terms, I would say still performance remains at the core of what we expect from a machine learning model. But then we need some other aspects, like uncertainty, which is basically in loose terms saying that the model should be able to say, I don't know. Or this is the amount I'm confident about this decision that I made. Explanation. In fact, European Union passed a regulation last year or earlier this year about the right to explanation, which is now actually we are, as machine learning practitioners, if we want to put the system into practice for certain domains at least, we are obliged to have explanation attached to our decisions that involves people's lives. Of course, the hard question on top of performance is to understand if this accuracy is gained by modeling the correlations or causalities. So this is very hard, but of course, if we can explain about the correlations and get the causalities, that will almost solve the problem of robustness. Logical reasoning, as we discussed, that's very important. That's part of how our brain works. And for example, again going back to object detection or visual recognition, we want to be able to have a system that can read the Wikipedia entry of an object for which it hasn't seen any previous images from, but able to recognize it in images. Like a description of an elephant, it has seen other animals. It sees the descriptions of elephant in text as it compares to other animals, and it should be able to do the logical reasoning of how to recognize an elephant in an image for the first time. So we need security on top of performance, which is being robust to illegal attempts. For example, in deep learning, there are two main tracks now which are very hot. One is that generally in medical data, in medical science and other fields, there are certain data sets that we are obliged not to publicize. But there are less strict regulations on the model that we train on those data sets. And there are works that has shown that you can actually sometimes reverse engineer the data that has been used for training those deep networks. So we should be able to manage those, encrypt them during training and things like that. Also, there are the notion of adversarial attacks, which is the models are sensitive to seeing samples that are inputs that are completely out of the distribution that they were exposed to during training, and they could completely confuse and make wrong decisions on those samples, and that there could be illegal attempts to misuse that aspect. Of course, for usability of systems, beside accuracy, we need computational complexity. We don't need a self-driving car that after hitting somebody says that, oh, I think I saw a man. So that's important, of course. Adaptability, again, goes back to changing distributions over time and the model being able to in an online manner, adapt to that change. So mainly in our group, at the moment, we're focused on these two aspects, uncertainty and explanation, both for deep networks. In this talk, I will okay, so first I want to say what do actually we mean by uncertainty. So it can be approached with two different questions. What are the sources of uncertainty, and what uses are there if we can have predictive uncertainty in our model? So the sources of uncertainty could be that we have in a very small data set. We know that the space of possible inputs or joint possible input and labels, can be highly multimodal in real world. So if we have a small data set, it means that we have every one of these modes gets low or no samples. That means that it's hard for us to actually in practice say for certain if a new sample and scene sample comes from the same distribution or not. We could have noisy inputs, since there are sensory problems all the time. That increases our uncertainty about the predictions. In the same manner, we could have noisy outputs, the same sensory problems, or also like there are annotation problems sometimes. The experts that provide the annotations, like again in medical science, they are very noisy, because actually in harder problems like like estimating the stage of a cancer, even different specialists don't have very high agreement with each other. So the labels can be quite noisy. So uncertainty is very intrinsic to those problems. The input could be incomplete. There could be missing data. Again, example in medical applications that some patients could not have gone through certain exams, which are key to the diagnosis or prognosis. And covariate shift, which is distribution of the domain changes due to time, location, going from one equipment to another, and things like that. So if we have a model that can output predictive uncertainty, what we can use it for? We can use it for active learning, which is because annotation, as we all know, is very expensive, especially when coming from fields that the annotators are like high experts of the society, which are rare and also very expensive to hire. So active learning, what it does is that it says that what is the most informative sample that I can take now and annotate so that it gives my model the most information. Uncertainty can help there. The higher the uncertainty of the model for a sample, the better the more the information you get from it being labeled. Exploitation in reinforcement learning, or generally in lifelong continuous learning scenarios, then you want to know when you think you know enough that you can actually exploit your knowledge now, or actually you think that you're unsure about so many things that you need to explore more in the environment. So sometimes the model is highly accurate, but the risk associated between different entities or different decisions is different. So we could have a high risk for something and very low risk for other things. The way that you can weight these different phenomena is by measuring uncertainty for those different things. So this comes in multitask learning, but also when there is different risk associated with different actions or decisions. Finally, model pathology. If you want to debug your machine learning model, that's where it becomes important. So now that we know there are like reasons to model uncertainty, I want to say what we actually mean by model uncertainty. So imagine a regression, general one-dimensional regression problem. The input is a d-dimensional vector, like temperature forecast, let's say. And the output is just one scalar. And we want to learn a parameterized function by theta, which takes us from the input vector to the output one-dimensional scalar. So now a typical deep learning model, if you give it like the data for all your sensor information today, and you want to forecast the temperature tomorrow, well, a standard one would just give you a point estimate of the temperature at the same time tomorrow. That can be useful, of course, but what will be more useful is to see how confident you are with this. If your model is really confident in the whole spectrum of possible temperatures, if it's very, very confident about this point estimate, or if it's kind of confident about it, it's not really confident, or it doesn't have any idea, as is in this purple line. So imagine if it was a point estimate and we didn't have access to these. There could be a very possible scenario that the point here, with point estimate here, have very negligible maximum probability, but because we just look at this point estimate, we could be really wrong. So Bayesian modeling is a common way of getting model uncertainty from the generally machine learning models or also deep networks. What it does is essentially for prediction of the label, you basically integrate over different possibilities of the model parameters. So we treat your model parameters as a random variable. We don't look at just the point estimate of that. And you integrate over different possibilities using the posterior that you learned during training, the posterior of the model parameters, given the training data. Of course, in that, there will be embedded the prior, but arguably the important part is integrating over different possibilities, and because of that, getting the uncertainty of probability distribution over the different outputs. So now going back to deep networks, there are different approaches to getting uncertainty from deep networks or Bayesian deep networks. One is to actually directly output the variance or some uncertainty measure beside your point estimate for the label. The other approach is put some distribution on the model parameters and try to learn or adapt those distributions to the training data. So there are lots of works for this scenario, but what we are interested in this work and the prior works to this, which I will explain, are the works that actually don't require retraining or redesigning the model architecture. So all these works require you to retrain or actually change the architecture of the network, retrain, and because of the necessity to actually propagate the covariance now, the training procedure is very time consuming. What we are doing in this work is different. So to explain what we are doing, I need to quickly explain what's stochastic, what I mean by stochastic regularization techniques. So regularization techniques are used to restrict the model families with certain criterion to avoid overfitting. Stochastic regularization techniques do so by having some stochasticity during training and for different samples. So you apply this, to in practice basically apply a different criterion on at different points during training or on different samples. Then it has been shown in this work that at least for one stochastic regularization technique called dropout, you can show that this a network trained with a stochastic regularization technique can be seen as an approximate Bayesian model. So following on that, we say that batch normalization is also a stochastic regularization technique, in the sense that your weight vectors are going through an affine transform. It gets subtracted by the mean of the batch and divided by the sigma. And these batches are stochastic. They change over during training time. So we show in the paper that actually you can see this, you can see a batch normalized deep network as a, again, as a approximate Bayesian modeling. So I have to say we do, like, as in like the original paper by Gal and Harmony, we make a few approximations and assumptions here. The important one is at some point we need to do an MC integral of one sample. But in general, we'll see that it works fine in practice. But I won't go through the steps of it actually showing it to be a an approximate Bayesian modeling. So this is the paper. It's still under review. So some results. First, we have some results on a toy dataset where there is a one-dimensional regression. This is the model for the original work of taking a dropout network as a Bayesian model, and you can see that you get, and these are the different confidence levels. This is the uncertainty that you get from the model for predicting these points. This is so the true function is something like an M, but these are the points that are generated from it, and you can see it's what we expect, that actually when there is no data point seen for a certain area in the range of in the domain of the function, the uncertainty should grow. Actually, this is very true, because if you retrain the model, it's very unpredictable what happens beyond this point. You see that for this training it has gone up, for this one it has gone down. So actually the uncertainty should be very high for unseen parts of the domain. While if you have like a model using just a constant uncertainty, you won't get this. Just assuming that there is a label noise, for example, that's not going to cover for it. So I will show you more results, but before that, I want to say that another thing we did is that generally it's hard sometimes to see, you see that there is some uncertainty output from the model and you measure it somehow, but it's hard to say if it's useful or not. So what we did in this work is to also show, propose two different measures for uncertainty that we think are useful. So one is a normalized measure. So PLL is a very common measure for uncertainty, which just is the sum of the log probabilities of the seen label, of the estimated label. So what we do is that instead of just reporting PLL, we construct a lower bound and upper bound, and we say, like, upper bound as in if we had a perfect uncertainty model, lower bound as if we did something very obvious. And then we see how much we are going from this lower bound to the upper bound, instead of just merely reporting the PLL. So the lower bound we just take as a constant noise predicted on the labels. So we assume IID noise on the labels, IID Gaussian noise on the labels. We estimate the variance, and then that will be the PLL that gives us, with that model, will be the lower bound. Kind of an obvious things to do. The upper bound, what we do is that assuming that the point estimate of the mean is fixed, we optimize for the best variance. So like the best variance that would give us the maximum PLL. If we knew somehow, we had an RKL, knew what that is, then what would be our PLL? Then we report the percentage points of how much we go from this lower bound to the upper bound. So we tried it on different data sets, the method, and these are shown in percentage points, like how far we can go from the lower bound to the upper bound. And the stars here are significance tests. So we've tried 5, if I remember correctly, 5 different random seeds and 5 different splits of terrain validation. Yeah, we have consistently positive, so that's good that we go beyond the lower bound, but you can see that it's still far from getting the perfect uncertainty, at least on some data sets. And you should know that this MCD, this is the baseline that we are comparing to. This is the work that has done the same thing on dropout networks. This is our work. And you should know that MCDO is actually, at the time that it was published last year, it was improving over many of the state-of-the-art uncertainty models on deep networks. So this is actually something that is considered good at the moment. But we should know where we are. So another measure that we introduced is a qualitative measure, where basically what we do is that we sort the test samples based on their predicted uncertainty. And then we show here on the vertical bar, we show the errors that was made on those samples. So ideally, you want to trend off the predicted uncertainty to follow the actual error of those samples, right? So here, the different shades of blue or purple are the uncertainty that we have sorted with. So it goes something like this. And this, the solid black line is some average kernel over the sample's errors. And you can see that at least it's kind of decreasing. It's kind of following the same trend for these 3 different data sets that we've shown here. And if you look at individual points, you see that like there is a drop in the error as you decrease the predicted uncertainty, which is nice, kind of. So we are on the right path, but we are far from being perfect. So we tried this to make it more tangible. We tried this method on a very standard computer vision task, which is semantic segmentation. Basically, what we did in semantic segmentation, we want to classify each pixel into different objects. So, and then what we did is that we applied, this was a batch normalized deep network. So what we did is that we applied this confidence, this uncertainty estimation on each pixel. And here you see the map for the norm of the uncertainty here. So as to be expected, the most uncertainty occurs when you're on the border of the objects. For example, there is a car, and when you go from car to building or from car to road, you get some uncertainty because the model is unsure. But also on the locations which there are lots of clutters, so the model can hallucinate lots of different objects here, for example, in the tree. Here is the uncertainty only for car class. So you see around the car, but also on the shapes that kind of resembles a car, which can be very useful. So it's like using it, it's just demonstrating how it can be useful in a very standard model. So this is based on the Bayesian segment model, Bayesian segment work of Kendall et al. In last year in BMC, I think. So I have to say, again, this is a model that can be used on any pre-trained deep network that either has dropout or batch normalization or both of them. You don't have to retrain your model. So if you don't care about the details of how it works, how it can be used in practice is very simple, actually. So basically, take any pre-trained network with batch normalization or dropout layers, calculate some constant observation noise, assuming, again, IAD Gaussian noise on the labels, call it tau inverse. Then at test time, you can sample different different stochasticity on your prediction. So basically, feed forward the same test sample multiple times. If it's dropout, have different dropout masks. If it's batch normalization, have different batch co-members with the sample in question and get different predictions. Then calculate the standard deviation and the mean of those different predictions. And then the point estimate will be the mean, and the uncertainty will be the constant label noise uncertainty plus the variance that you get from this. So that's it. That's all we did for all those previous results that you saw. So it's very simple, very useful. And the reason that we try to do it for batch normalization is that it actually, in most of the modern deep networks, you just have batch normalizations instead of dropout. Although dropout is always useful, it's become less common to use it. But batch normalization, you see it on all modern deep networks. Okay, so just to quickly go through the one medical application that we have and how we use uncertainty there. We work on a project for mammography. So in mammography, women in Sweden are between age of 40 and 74 are called every 18 to 24 months. And the mammogram is acquired from multiple views from their breasts. And then two radiologists look at these mammograms, make a decision. The decision is of each is taken to a board, and then the board discusses, either decides that this is healthy, or that it needs actually more investigation. And with more investigation, it could lead to a cancer diagnosis. So we know now that we have a very bad situation about the shortage of radiologists for this. And so for that, the first thing to think about is the CAT system, which does this detection of the cancer in mammograms automatically, which is the accuracy I was talking about. So we've done that. We have a quite accurate tumor localization system because of so much data that we've been able to collect from Karolinska Institutet, and also like the collaboration with SLL. But that's not the only problem. There are like 28% of cancers that are diagnosed are interval cancer. And what are those? Interval cancers are the ones that are detected, diagnosed in between two screenings. So these are the cases usually of very fastly growing tumor. So it was very small, but also the cases that the breast density or the amount of compression, the way that the breast was situated in the equipment made it very hard for the model or basically for the radiologist to actually make a decisive conclusion. So for that, we basically use our uncertainty in these scenarios. To predict that if it was hard to get the diagnosis. So that's very useful. That's how we use uncertainty. And then we could go through a further MRI where things are much easier detected. Also, as I said before, an active learning, hiring a radiologist for annotating our images is hard. So with uncertainty, we can provide lower number of images to them with highest uncertainty and ask them to annotate them. This is another track we are looking into. But also, as I explained for the computer vision, the semantic segmentation example, we want to use it for getting a better CAD model. Of course, this uncertainty helps for that. So another thing we do is in our group is explaining the decisions, which is also relevant for medical applications. But due to the interest of time, I think I'll skip that. Thank you.